Section 5.5, we study about substitution, right? Section 7.1, what did we study? Yes, integration by parts, review them. Section 7.2, what have we done? Right, integral of Greek functions. Okay, review them. Section 7.3, because we have already reviewed these already, so I just want to give you the summaries of everything we've done. And now we need to deal with the radical signs, right? Yeah, trig substitution. Very good, thank you. So now today we will study the section 7.4, integration of rational functions by partial fractions. Okay. Suppose we need to compute integral of a fx function here, which is px over qx. So where p and q are polynomials, and the polynomial has a forms of this guy. Okay. So if the degree of this polynomial is the highest order of the x variable here. In this case, for example, the highest order is x to the n, right? So this is the polynomial of degree n. Okay. If the degree of p is less than the degree of q, then we call it a proper rational function. Okay. If the degree of polynomial p is larger or equal to degree of polynomial q, we call it improper. That's it. For example, let me quickly go over everything in the section, and we go to details later, okay? Give some ideas about this. And the first forms is, if it is like this, we can somehow do the long division to write another forms of the f function. First thing we study. Then, if the case one, if the denominator qx is a product of distinct linear factors here, we can write the function fx over equal to p over q would be like this terms. That is the first case we study. Okay, and here are some tricks to find this expression. And the second case, when qx, the denominator, is a product of linear factors and some of them are repeated. For example, the denominator somehow there's a1x plus b1 to the r, it is repeated r times here. Then we know how to rewrite this fractions. That is the second case. The third case, when qx contains an irreducible quadratic factors here, quadratic functions or the polynomial of degree 2 is the polynomial like this, and it is irreducible when the discriminant is smaller than 0. In this case, we can write the rational function is this guy, for example. That is the third case. Here are some more examples. And the fourth case, when the irreducible quadratic functions are repeated, it means that it is of the degree raised to the power of r. Then we know how to rewrite this fractional functions. These are all the possibility that we have of these types. So now let us go to details. Okay. First, suppose we are given this example right here. Example 1. So first, we need to find this guy. Okay. We want to do this. Now, from the above definition, is it a proper polynomial, fractional, proper fraction or improper? Here, right? This rational function is improper here because the degree of the numerator, the highest degree is 3, and the degree of the denominator is a linear function, which is degree of 1. So what we should do is to do the long division. Okay? And it's like dealing with numbers. Okay? Similar. So if you don't remember, let us do it together. Suppose we want to find the relation. We want to divide x cubed plus x by x minus 1 here. We write it this way, right? What we should do is to take the highest degree here, this guy, divided by the highest degree of the denominator here, the divider. And what do we have? X squared. Very good. Thank you, Luke. This is x squared. Why? Because x cubed divided by x will be x squared, right? So we multiply back this guy, we multiply the whole things here, but now we rewrite it below this guy. What do we have? If x squared times x, what do we have here? Very good. And x squared times -1. Very good. Okay. Thank you. So what should we do now? Yeah, we subtract. And at this step, we will do subtraction right here. Okay. Remember, we subtract the whole things here. So be careful with the sign.
Should it be minus x squared?
Oh, thank you. Yeah. Very good. Thank you, Charles. So if we subtract, then x cubed here, subtract x cubed here, and it will be. And at the order 2, there's nothing on top of this. And negative of negative x squared, what do we have here? Negative of negative x squared, right? It becomes, be careful with the sign. Okay, very good. So what is next? Yeah, and this guy. We need to rewrite it. Okay, is it clear to this point? So now the similar process will be repeated. Now we consider the highest degree of the remainders here. And what is it? This guy. Very good. Divided by this guy, right? What do we have here? Yes, we have x here. Very good. Remember the sign here. This is positive divided by a positive. Then this guy becomes positive. Okay? Very good. The same things. We multiply back here, right? Yeah, I don't want to mess it up. Just imagine, do it in your head. Or let me use a different color. This guy multiply with this guy, and this guy multiply with the -1. So it will be very good. X squared minus x. Who was that? Victoria, thank you. So we have this already, right? So again, we do subtraction here, right? Then x squared minus x squared, what do we have here? Yeah, very good. 0. Here, x minus -x. Very good. Plus 2x here. Very well. So now, what should we do? Yeah, because 2x, if we do this, okay, let's continue, it's fine. But we can stop, we can definitely, okay, let us continue. 2x divided by x give us 2, right? Then again, we multiply back, it will be 2x minus 2, right? Very good. Then subtract, right? It will be very good, plus 2. So this is the remainder, right? Very good. Okay, so therefore, we can write, it means that x squared plus x here divided by x minus 1 will be this guy, the green one here, x squared plus x plus 2, right? And very good. Thank you, Aluk. Beautiful. Plus 2 divided by this guy, right? So, are we good? How do we know that our computation is correct or not? Yes, we can double check it, right? If you want. What you can do, just imagine, right? Imagine that this guy is a terms, we multiply with 1, which is x minus 1 here, right? Then distribute it, add them up, and you see it will end up the same things, I cube plus x, okay? But if you're confident with your computation, you don't have to double check it, okay? But if you want to, then this is how we do it, okay? That's it. Very good. So it means that in order to compute integral of x cubed plus x here divided by x minus 1 dx, it will be the same as integral of right. Okay. Then we take antiderivative of each of this guy, and what do we have? First, this guy. Very good. 1/3 x cubed. The next one? Oh, yeah.
Oh, wait.
Yeah. So antiderivative of x to the 2, it would be x to the if we want, we can write it. Imagine antiderivative is the reverse things of derivative, right? We add one more orders here and divide it by the same numbers, which is 3 here, right? The second terms will be, yes, 1/2 or this guy, yeah. And the third one, very good. And the last one,
2 out of x minus 1.
Charles, right?
Yeah, 2
Very
out
good.
of x minus 1.
Very good. Okay, you can do some substitution here, right? But it will, because I suppose that we all do it and get used to it already. And we have this result. And remember to add a constant. Okay? Remember here, this guy, we should take the absolute sign here. Is there any question with this one? Are we good? Clear? Very good. That's it. Okay. So, but life sometimes is not that easy. Sometimes in the denominator, there are multiple terms, right? They are a product of many things. And this, the first case, suppose the denominator is a product of linear functions, which is the polynomial of degree 1, the first term, second terms, etc. Okay, then how can we do this? And some great mathematician has already proven this, that we can always separate this and we can rewrite it as this form, where a1, a2 to ak are numbers. Beautiful, right? It was very complicated and it's hard to find integral. But now if we break them into small pieces here, things becomes a lot easier, okay? Now, let us take a look at this example. The example 2. The denominator first, is it a rational, this rational function, is it a proper one or improper one? Proper one, right? Because it's proper one because the degree of this guy is 2, of this guy is 3, so we don't have to do long division, okay? But now, the denominator, let us take a look at this. So, can we write it as a product of linear functions? And how can we do it? Now, if you don't know, just take a look at these guys. What is the common things of them? Yes, every term here has an x, right? It means it is a common factor. Let us factor it out. What do we have inside? Very good. Okay. What should we do here? Yeah, how can we factor it? Have any idea? Uh, say it again. Like this. Interesting. How can we know? Yeah. If we multiply it back here, this guy will be 2x squared. This guy will be 4x. This guy is negative x, so some of them would give us 3x. This negative 1 times 2 give us negative 2. This is a perfect way to factor it, right? But is it the only way? But sometimes we don't know how to factor it. You've done it beautifully here. We know the result. But how can we go from here to here? Suppose we have no idea. Right? Remember, this is a very important properties. You can write it out. If we're given the function f of x, which is a x squared plus bx plus c. This function, polynomial, we can always write it as the polynomial here. Suppose it has two solutions, okay, x1 and x2. Then we can always factor it as ax minus x1 times x minus x2. Okay, keep it in mind here. So now take a look at this quadratic function here. A in this case is 2, B is 3, C is negative 2, right? So the discriminant of this polynomial, we call it D, is this formula, right? And what is it in this specific case? 9. Right? So what do we have here? 9 plus 16, which is, and we know that x1 will be minus b plus square root of d over, which is negative 3 plus 5 divided by 2. Yes, it will be 2/4 or 1/2, right? Very good. This is the first solution. The second solution will be right, and what is it? Negative 2, okay? We know the two solution. Let us apply to this guy, okay? Therefore, let us say fx is 2x squared plus 3x minus 2. So therefore, we conclude that fx is 2x squared plus 3x minus 2. Oh, we can write it as 2, this is a, right? X minus x1, which is x minus, it will be plus 2, okay? So if you distribute this guy to here, what do we have here? and this, right? It is exactly the same as what we have here. Okay, this is another way how to find it properly. Or if you are as smart as him, and many people in the class have done it, you can do it very fast by doing some trick. Okay, review this yourself. But now, let us continue. Okay, it means that this integral x squared plus 2x plus 1 divided by the denominator, and the denominator becomes this guy, right? Okay, we can rewrite it this way. So we place it here. This is -1, right? So the problems becomes this guy, okay? Go back to the strategy for the case 1. What do we have? Look at this. They say that we can always write this guy is the sum of these, okay? And in our situation, we have 3 terms here, okay? It means that we can write this integral. Let us do a side computation and add it to the integral later. Okay. Or side computation here. So we can write this guy is A over the first guy plus B over the second guy plus C over the third guy. Okay? They say that. And our job is to find A, B, and C. Okay? How can we do that?
I don't know how to describe it, but like maybe, so you said like x squared plus 2x minus 1 equal a times 2x minus 1 times x plus 2 and plus b times x plus 2.
Very good. Let us do it slowly. Very good, Corner. So we know that this guy is A over x. If we multiply it by 2x minus 1, x plus 2 here, does it make any change? They're the same as the previous one, this guy, right? Because this term is simply 1. Nothing has changed yet. We can do the similar things, right? B over 2x minus 1. But now, in this case, we have the same denominator with the left-hand side here, right? So that later we can compare the two fractions, okay? But here, B, what should we multiply here? Very good. We just multiply with the other two denominator. Very good. Good job. And the last one? What do we do? Very good. Okay, good job. So what should we do now? Yeah, let us distribute it and compare the two fractions on the left and the right and see, right? Okay, if we multiply it here, a times distribute this, it will be, this is 2x squared plus 4x minus x here, right? Minus 2, okay? And the denominator, which is x 2x minus 1, x plus 2, okay? But instead of writing this, let us write it this way. If we multiply both sides by the same denominator, then we have x squared plus 2x minus 1, right, on the left-hand side. Should be the numerator of these on the right-hand side, sum of them, right? So the second terms will be b times, what is it? Very good. And c times? Very good. Okay. We do two things at the same time here, but is it clear for you all? Any question? We multiply both sides by the same denominator, right? Then the denominator here will cancel each other. Okay. Then what is left are they here. Okay. Very good. Now, okay, on the left, there are some terms of x squared, some terms of x and numbers here. On the right-hand side, let us factor the terms of something related to x squared, right? Okay, and add them up. What do we have? Suppose something times x squared. What are they, the coefficient here? We multiply it here. Look at this. Yeah, it's tricky because in front of that there's a coefficient a here, right? It would be 2a, and here. Very good, Jacob. And the last one is 2c. Okay? Are we good with this one? Do you all see why we have this coefficient? Very good. Then we do with the second, guys, the coefficient of, the coefficient of the orders degree 1 here, right? Okay, we need to find them, which is of order x here. What is it inside? Yeah, 4 minus 1 here give us 3. 3 and then multiply with a in front of that, it becomes 3a. Okay. In the second terms here, 2b, very good. And minus c, very good. For the numbers, what do we have? numbers, we have this guy, right? So minus 2a. Okay, that's it. Now, they are both polynomials. The left-hand side, we know the specific coefficient. The right-hand side is also a polynomial of degree 2. They are the same. Therefore, the coefficient should be the same, right? Therefore, from this, we know that, okay, this guy should be very good. This guy should be 2. And this guy will be very good. So in the end, we conclude that, okay, we know for sure that 2a plus b plus 2c should be this coefficient, which is 1. The second terms here, 3a plus 2b minus c should be 2. And the last term here, negative 2a, should be negative 1. Okay, now if we can solve this system of equations, then we know a, b, and c. There are 3 equations for 3 variables, a, b, c, so it is solvable. In the first, let us call 1, 2, 3 here, right? So first, in the third equation here, what do we have? A is equal to negative over negative 1 over negative 2, which is 1/2. Very good. Okay. If we know A, right, then the equation 1 and 2 becomes, the equation 1 becomes 2 times 1/2 and plus B plus 2C is equal to 1, right? The second equation becomes 3 times 1/2 plus 2b minus c becomes equal to 2, right? So I believe that from now, you can all solve it yourself. Go home and double check it yourself. And for here to save time, let me just write the value of A, B, and C. Okay. Do some more computation. We know that A is 1/2, B is, let me see. B is 1/5. C is negative 1/10. Okay, we know A, B, and C. Let me go back here. Therefore, we have dx is equal to, this guy is 1/2 B is 1/5. So C is negative 1/10. They all multiply with the term dx here. Okay. Now it becomes sums of simple integral, right? The first one give us, what is it? the number 1/2 is fine. Integral of 1/x will be, what is it? Thank you, Charles. Very good. And the second terms here. Why do we need to multiply with the number 2 here? Yeah, the chain rule here. You can do substitution and double check it, but I suppose that you can master your skill and look at that immediately. And the third one, right. And what do we need to do? Yeah, plus C, where C is in R. Okay. Okay, is it clear? Make it simpler and solve each of them. Very good. And here, it is a very beautiful note. Instead of solving the system of linear equation, we know that this relation is true for any x, this equation. Therefore, it is true for some specific value of x. So let us choose. If we put x is equal to 0 here, look at this term. We have this guy, right? If we consider when x is equal to 0, then luckily, this term will disappear. This term will disappear, right? The left-hand side will become a number, and the right-hand side, we replace x by 0, put it here, we can find it easily that a will be 1/2, a lot faster. Okay? A second case, we consider x is 1/2, which is the solution of this guy. Then if we replace x by 1/2, a and B, c will disappear. And we can find b easily. And it is 1/2, or 1/5. Similarly, if we substitute the value of the solution of this term, a and b will disappear, right? And the left-hand side will become a number. The right-hand side will be simply c times solution and this. And you can find c to be this guy easily, okay? Is a lot faster. So tomorrow we will continue doing some more examples. Very good, and see you tomorrow.